partner for RO Electronics. They'll be presenting here today on condition-based monitoring, which is absolutely critical to manufacturing and how to make manufacturing more efficient and to use less resources. So I'm going to hand over to David. David is RO's marketing manager for our analog devices. So David, take it away.
Thank you, Gary. Good morning, everyone, and welcome to this morning's session. This morning's session's split into two parts. In the first part, we've got Chris Murphy from Analog Devices, and in the second part, we've got a couple of guys from a company called SureTech. This morning, we're going to cover the benefits of implementing Cbm solutions, system design considerations, and also solutions and platforms in order to sort of start development quicker and easier. There's a number of people on the call this morning from both Analog Devices and Arrow. So as mentioned before, if you do have any questions, please pop them in the chat and we will do our best to answer them. So without further ado, I shall start this morning's presentation.
My name is Chris Murphy. I'm an applications engineer with Analog Devices, focusing on condition-based monitoring. In the first half of today's session, I will discuss why condition-based monitoring is important, what sensors we use to detect faults. We will look at condition-based monitoring, data acquisition, signal chain solutions for MEMS and Piezo sensors, as well as reference designs and platforms showcasing Analog Devices' range of CBM-specific solutions. Next, we will look at what condition-based monitoring is and why it is important. Condition-based monitoring, or CBM, involves monitoring of machines or assets using sensors to measure the current state of health. Predictive maintenance, or PDM, involves a combination of techniques such as CBM, machine learning, and analytics to predict upcoming machine or asset failures. What are the advantages of a condition-based monitoring system? A lot of industrial motors are designed to work for up to 20 years in continuous production applications where they perform a critical role in keeping production online. A lot of these motors don't reach their projected lifetime. PDM enables maintenance teams to schedule repairs and avoid unplanned downtime, leading to increased productivity. Early prediction of machine faults through PDM can also help maintenance engineers to identify and repair motors running inefficiently. For example, a cutting machine with excess vibrations could lead to poor quality products. Identifying and remedying this early leads to increased performance and product quality, further increasing productivity through less scrapped parts. Early prediction of machine faults can also lead to increased asset availability and lifetime by reducing unnecessary wear and tear on mechanical elements. Inherent in this early fault detection is the reduction in risk of a catastrophic failure where infrastructure or even people could be damaged or injured. CBM is vitally important to Industry 4.0 and ensuring production is as efficient and reliable as possible. Condition-based monitoring enables us to detect faults. Let's take bearing issues as an example of a motor fault. According to a Wall Street Journal post, unplanned downtime costs industrial manufacturers an estimated $50 billion annually. Using predictive maintenance to limit this cost is critical in highly competitive manufacturing industries. Unplanned downtime in just one machine in a just-in-time manufacturing environment can cause delays that lead to unhappy customers, possible loss of those customers to a competitor, and a direct hit to a company's profits. In order to minimize production downtime, it's imperative to know about the potential failures within the motor or the asset in order to be ready to deal with them. Bearings are a key failure element in the vast majority of industrial rotating machinery, as shown in the pie chart. What this tells us is that any CBM system intended for use on rotating machinery should focus on bearing analysis as an early indicator of potential faults. This slide shows a simulation of a faulty bearing in a critical asset and corresponding FFTs or Fourier transforms of the fault signature over time as the fault worsens. Bearing faults first appear at high frequencies with a very low amplitude. For predictive maintenance, measurements are made up to 10 kHz and beyond because vibration components of interest first appear at higher frequencies. The highest performance sensors are required for predictive maintenance, shown here in green, where we can detect the bearing fault at the earliest possible time. Over time, as the fault worsens, the fault frequency modulates down to lower frequencies around 5 kHz or less, and we also see an increase in magnitude. Medium performance vibration sensors can detect these faults, shown in orange. Medium because these sensors are not capable of detecting faults at the earliest point in time due to having smaller bandwidths and higher noise. These sensors are likely to be deployed on less mission-critical assets. At this point in time, the fault has worsened, so it may also be possible to detect increased bearing temperatures or particles due to excess wear. When the defect frequency approaches the natural frequency of the motor at less than 1 kHz, the magnitude has increased significantly, as has the noise floor. Low performance sensors can be used for detection here as noise and bandwidth requirements fit those of general purpose accelerometers, but it should be noted that motor failure is much closer if you wait this long. The easiest machines for bearing fault detection are those where sensors can be mounted directly on bearing housing and where there is little vibration from other machine components. On machines like compressors and pumps, we see more vibrations from other machine parts, so we need to use higher performance sensors to detect fault vibration data. For industrial gearboxes, sensors can no longer be placed directly on the bearing housing, but they can be placed on the transmission path from internal bearings to the housing. Because we must place the vibration sensor further from the source, it's imperative to use a higher performance sensor. Likewise with turbines and more complex mechanical systems. Next, we will look at some vibration sensors for Airy fault detection. Here we can see a table of machine faults and sensor requirements to detect those faults. On the left, we can see imbalance and misalignment can be detected with lower performance sensors. Fault signatures appear at lower frequencies, down to 1 kHz and below, and higher magnitude. So a low bandwidth, higher noise sensor can be used up to 1 millig per root hertz. For bearing and gear faults, high performance sensors must be used to detect faults early. We need a noise density of less than 100 microGs per root hertz and a bandwidth greater than 5 kHz or even higher depending on the asset. Making wide bandwidth, low noise MEMS accelerometers is very difficult. At the moment, analog devices are the only MEMS manufacturer to produce accelerometers that can compete with piezo sensors, the gold standard vibration sensor used for decades on the most critical assets. This table shows a wide range of accelerometers in terms of performance and capabilities for CBM, from a simple 3-axis analog output accelerometer on the left to an intelligent edge node module for semi-autonomous condition-based monitoring on the far right. High-performance sensors are shown in green, and these were designed specifically for CBM applications. All other sensors are targeted at either high-performance automotive or industrial applications, but are still highly suitable for use in vibration sensing due to their low noise and wide bandwidths. For example, the ADXL 317 has a bandwidth lower than 5 kHz at 4 kHz, but a noise level well below 100 microGs per root hertz on the X and Y axis. Likewise, the ADXL 356 and 359, making them ideal for CBM applications. In this table, I'm comparing MEMS accelerometers and MEMS microphones to the gold standard early fault detection sensor, piezo accelerometers. Data in each column is representative of the minimum or maximum variation within that category and doesn't correlate to adjacent columns. The piezo sensors have the best noise performance, but at a cost. Their bandwidth is also excellent, up to 30 kHz and beyond. But Piezo have no integrated features, and power consumption is not ideal for wireless condition-based monitoring installations, even though some parts do have power consumption down as low as 200 microns. MEMS accelerometers for predictive maintenance, as you would expect, are more expensive than general purpose accelerometers. Making wide bandwidth low noise accelerometers is not easy. The bandwidth is ideal for PDM applications, but not as high as Piezo. MEMS accelerometers are the only sensor with a DC response, useful for slow rotating machines and for detecting tilt. They're also the only sensor with a self-test feature, which can verify if the sensor is still functional once deployed. This might be advantageous for safety-critical applications. Microphones can detect from tens of hertz up to 100 kilohertz for ultrasonic microphones at a very low cost. MEMS microphones, along with MEMS accelerometers, are ideal for wireless condition-based monitoring systems. Accelerometers are the most commonly used vibration sensor, and vibration analysis is the most commonly employed PDM technique. It is possible to completely seal MEMS accelerometers hermetically in ceramic packages and piezo accelerometers in mechanical packages for use in harsh, dirty environments. This table focuses on physical, mechanical, and environmental performance of the sensors. This is where the key differences can be seen between each sensor, such as integration, tolerance to harsh environments, mechanical performance, and attachment to a rotating machine or mount. Piezo accelerometers have industry standard interfaces like IEPE and 4 to 20 milliamp. These sensors are packaged in a mechanical module that can withstand vibrations and shocks without affecting performance and can be mounted or connected to industrial machinery with ease. They also have excellent performance in harsh operating environments. In benign environments, MEMS microphones offer excellent performance for PDM applications. Currently, there's a lack of information available on mounting MEMS microphones in harsh operating industrial environments with excessive vibrations, dirt, or humidity. MEMS microphones have shown distortion of up to 8 dB when exposed to increased humidity for prolonged periods. Analog devices have pioneered MEMS accelerometers for use in PDM applications and continue to deliver industry firsts, namely MEMS accelerometers in mechanical packages or on mounting modules where the frequency response of the sensor is maintained when it's mechanically attached to an asset. MEMS sensors with industrial interfaces like IEPE and 4 to 20 milliamp capable of being retrofitted into a piezo mechanical module. MEMS accelerometer performance and stability in harsh environments is also excellent, just like piezo. Next, we will look at some customer pain points when trying to use MEMS sensors for CBM. For example, attaching MEMS sensors to assets and interfacing with existing piezo infrastructure. The ADXL1002 is an industry-leading ultra-low noise and wideband MEMS accelerometer, and it's a viable alternative to piezo accelerometers with comparable noise density, superior performance and temperature sensitivity, DC to low frequency response, phase response, and group delay. For customers to easily evaluate and replace piezo accelerometers with the ADXL1002, we designed an interface that is compatible with IEPE, the de facto standard piezo sensor interface. Both of the sensor PCBs shown are circuits from the lab reference designs available from analog.com. The sensor interface PCBs were designed a little thicker than normal in order to maintain the datasheet performance of the MEMS accelerometer. Extensive characterization was performed to ensure this. The reference design PCBs can be fitted to a piezo mechanical module and retrofitted and powered by existing piezo infrastructure. The aim with the IEPE and 4 to 20 milliamp reference designs was to make it very easy for designers to implement a MEMS sensor in place of a piezo sensor. But please note, analog devices do not make the piezo modules. A However, a stud-mountable cube is supplied with the reference designs to allow immediate testing out of the box. The mounting cube, along with PCBs, solder plates, etc., have been extensively characterized to ensure datasheet performance is maintained. These solutions make it very easy for CBM designers to attach MEMS accelerometers to their assets, as well as seamlessly interfacing with existing Piezo infrastructure. So with that information in mind, this begs the question, should I use an analog or digital output accelerometer for PDM applications? You can see the range of accelerometers and their effective resolutions for use in CBM applications. Beyond 14-bit, the designer has to work with analog output sensors. Piezo accelerometers have dominated this space for decades, but recent advancements in MEMS technology, pioneered by Analog Devices, have enabled MEMS accelerometers to now compete with Piezo. The ADXL1000X family of MEMS accelerometers and Piezo accelerometers offer the highest possible performance for vibration sensing, and both sensor types are analog out. This means for CBM applications requiring the highest performance, the designer must consider the full analog data acquisition signal chain too. Here we see another CBM reference design. Piezo accelerometers are a focused sensor for our precision signal chain. Here we can see an IEPE piezo accelerometer signal chain example. This is an optimal signal chain tested by Analog Devices to achieve the best performance. We can provide current sources to power the piezo sensor, precision power to maintain stable low noise performance, wide bandwidth low noise amplifiers, ADC drivers to work with the atypical power supplies, and precision ADCs with wide enough bandwidth, speed, precision and filtering to maintain the fidelity of critical vibration information used to keep factories running. CBM system designers using piezo accelerometers require a high-performance analog signal chain to maintain the fidelity of the vibration data. Designers can evaluate the signal chain performance out of the box simply by attaching their IEPE or their ADXL1002 IEPE sensor to the reference design. Analog Devices have put significant effort into validating this design to make the designer's life easier. Design files are available, highlighting precision parts and allowing for easier design into end solutions. Analog Devices' precision signal chain micromodule portfolio combines different technologies like programmable gain instrumentation amplifiers, ADCs, DACs, switches, muxes, and so on, along with our high-precision iPassives technology via system-in-package to deliver a more complete data conversion solution. Micromodule devices simplify the task of developing high-precision measurement solutions by transferring the design burden of component selection, optimization, and layout from the designer to the device. Micromodule solutions reduce system-level development cycles and significantly reduce the PCB footprint. They also reduce total cost of ownership associated with manufacturing yield and support due to more of the signal chain being covered by just one datasheet. The next 3 slides are presented just as a brief overview to make you aware that we have reference signal chains available for specific purposes, like low power, like small size, utilizing our micromodules, and multi-channel for both MEMS and piezo accelerometers. And we're more than happy to discuss the requirements around these signal chains. The circuit shown only requires 7.21 milliwatts of power while it's offering high performance, so it's ideal for use in high performance wireless CBM systems. For designers requiring small solution size for space-constrained designs, along with high performance, we have several reference signal chains available for single and multi-channel solutions. Here we have a compact single-channel piezo accelerometer reference design suitable for advanced CBM. This circuit works with a multitude of IEPE accelerometers from multiple vendors. A multi-channel version is also available, and these have been tested and verified to offer the best performance. Next, we look at some reference designs and platforms that showcase Analog Devices' commitment and capabilities to provide best-in-class CBM solutions. Analog Devices' wireless CBM platforms highlight our low-power, high-performance signal chain, as well as mechanical attachment capabilities that help to maintain wide bandwidth performance. There are two options available. On the left, a 1-axis 10 kHz bandwidth, or on the right, a 3-axis 1.5 kHz bandwidth solution. These wireless solutions come with a complete signal chain for precision data acquisition, including the sensor, ADC, low-power processor, low-power wireless radio, as well as the graphical user interface. The mechanical design allows for stud or magnetic mount to an asset for improved high-frequency vibration performance. This enables quick attachment while minimizing packaging resonance. Wireless communications is based on the Smart Mesh Robust Wireless Communications Link. This is a low-power mesh network enabling wire-like reliable time-stamped communication. Utilizing a CBM platform like this can accelerate time to market. All the hardware and software design files are available for customization and development. It should be noted that this development platform is only for evaluation purposes. There's also a Python-based GUI for data collection and for learning about your asset. This slide shows one of our wired CBM reference designs. On the left, we can see the ADCM, CM for condition monitoring, XL3021 or 3021. This contains 3 single-axis MEMS accelerometers, the ADXL1002, 3 ADCs, a processor, memory, and some algorithms, all in a mechanical module with a resonance over 50 kHz, so well away from the bandwidth of interest. This highlights the capability of MEMS accelerometers to integrate intelligence at the sensor node, ensuring the sensor is paired with the best signal chain and processing to achieve the best performance possible. This module can perform FFTs, trigger various time domain or frequency domain alarms, as well as generating time domain statistics vital for algorithms or machine learning tools to predict failures. On the right, we can see the reference design enabling robust wired CBM solutions. So this is RS485 data and power over SPI. This offers noise immunity across long cables up to 100 meters. Several variations are available based on system requirements and solution cost. This reference design can also include access to an off-board low-power processor for custom protocol and application design. The software tool offers an easy-to-use environment to characterize and understand your asset's behavior. Typically, CBM designers initially use a high-performance sensor to understand their asset or motor, such as the ADCM XL3021. Once they have developed machine learning algorithms, they may be interested in testing lower performance sensors until they reach a good enough level of performance for an embedded solution. This wired CBM evaluation system also works with all of the SPI output accelerometers listed on the left, so it can be extended to work with an entire range of sensors, offering greater design evaluation flexibility. The machine learning kit is targeted at designers wanting to understand their asset. Typically, as a first step in developing machine learning algorithms, designers need to collect a lot of high-quality data in order to understand the baseline of their asset, and then match mechanical anomalies to anomalies in the data and begin the machine learning process. The machine learning kit enables this process out of the box. It consists of multiple reference designs. When combined, they create high performance and flexible machine learning platform for monitoring pumps, fans, motors, and other assets. The accelerometer sensor data is output in the popular IEPE format, so designers looking to replace piezo sensors have an easy way to directly compare. The data acquisition board provides a full bandwidth data pipeline into the FPGA where the system can monitor the data profile of the machine. A Linux oscilloscope application running on the FPGA, so there's no PC required for this system, provides frequency spectrum information and allows users to quickly visualize the machine's health. Python and MATLAB bindings enable designers to directly interface the machine learning data into these popular tools. Designers can then take their machine learning data and start creating algorithms for their equipment to better predict failures, for maintenance plans, and to avoid potential factory downtimes. And for more information on any of the CBM solutions shown today, please contact me on christopher.murphy@analog.com. So there are 4 new reference designs or platforms that are either just released or about to release in the coming quarter. Analog Devices are committed to enabling you to keep your customers' factories running. For more information, please visit analog.com/CBM. Thanks for listening.
Hello everybody. My name is Thomas Müller, and I'm running the German branch of Sheerotech Solutions. I'm located close to Frankfurt, and I'm in charge of sales and marketing for Sheerotech. Today I'm doing this presentation about our Icomox solution together with my colleague Guy Zoha, who is our head of R&D and one of the fathers of the Icomox. He's located in Israel, close to Tel Aviv. Please contact us anytime if you have technical or commercial questions. Thank you. Let's have a quick look on our agenda for today. I will give you a short introduction about Sheerotech Solutions and the concept of the Icomox. And Guy will take the technical part, starting with the Icomox architecture, our cloud and services, and we will finish our presentation with around 10 minutes live demo video. Just a quick snapshot about our mother company. Sheerotech belongs to a well-established company in Israel. AY Electronics has more than 40 years experience in component sourcing, supply chain management, and contract manufacturing. We are working with partners around the globe. The benefit for you, if you want to have a customized product, we can offer all needed services in-house. From the hardware design, component selection, sourcing, manufacturing, everything will be provided from a single source. We are working with tier 1 partners like Airy Electronics and for sure Analog Device, as well as with many others. We launched our product beginning of 2019 in a time where the market for condition-based monitoring solutions already lifted up. Due to the Corona crisis, this market got another boost. Shop floor and maintenance managers are looking for remote services to control their machines and assets. By using a CBM solution from Sheerotech, you can increase efficiency, save costs, improve product quality and the safety of the employees with your existing set of machines. Today we are talking about our Icomox, an intelligent condition monitoring box. We developed this box together with the Airy Electronics and Analog Device. Icomox is a retrofit solution which can be easily installed on motors or assets. Icomox is an open platform and the product can be customized based on your needs. From our webpage, you can download the latest firmware and the monitor application as well as the SDK packages. Based on the feedback we got from factory side, our integrators, and as Chris from ADI mentioned, most of the production machines are on duty for more than 20 or even 30 years. They are working in a complete offline world. The machines are managed manually and the site manager needs to do visual inspections. Machine running times or failure reports are even done on paper. The Icomox is offering a complete setup to bring your asset to the online world. It's a pre-configured hard and software solution with a microcontroller connected to 5 sensors. With this solution, we are offering a complete infrastructure to start data acquisition and condition monitoring of your assets. In combination with our management software, we offer an end-to-end solution to visualize the performance of your assets and to give you a tool to optimize your maintenance cycles. When I'm visiting customers or trade shows, it seems like the use cases are almost unlimited. The customer understands the concept quickly, and they are coming up with many potential use cases which you would never think of. Some of them are even not related to motors, pumps, or generators. They are related to buildings, bridges, or structures. You can easily install the Icomox in windmills, water plants, elevators, and many other industrial or even non-industrial applications. Just as a quick rehearsal of our Icomox concept. We have 5 sensors on board. Guy will give you more details about it later on. We do true edge computing with machine learning and smart AI on the device. Additionally, we can offer you an AR, VR maintenance software to guide technicians how to install the Icomox or how to repair your machine. If you have interest on this software, please give us a call later on. Last but not least, we have 4 connectivity options. We have Smart Mesh, powered by ADI, NB-IoT, and Power over Ethernet. Additionally, every Icomox box has a USB-C connector for permanent data streaming. As of today, we are offering 3 different models of the Icomox. They are all available off-shelf from Airy Electronics. We have Icomox Power over Ethernet. It's a wired solution and a perfect match for permanent data collection. It supports high raw data bandwidth for industrial environment. The second option is Icomox NB-IoT. It's a battery-powered wireless solution for once-per-day data collection. You can use it for outdoor environment or remote installations like windmills or water plants. The third option is Icomox Smart Mesh. It's an ultra-low power, battery-powered device with a high reliable communication protocol, powered by ADI. The next 3 slides are showing some use cases. The first one is from the oil and gas industry. Here we did an installation for a test center of valves. After 5 minutes installation, the technicians have been able to see the sensor data of the inlet and outlet gas pressure, as well as the condition of the valve. It's a retrofit solution without affecting the given installation. So it was really quick to show the technician the actual data with our Icomox. The second example is from the Netherlands, where we did an installation in a huge warehouse to ensure high utilization of the conveyor belts. With the Icomox, the maintenance manager is now able to check the condition of the installed motors with our monitor application in his office. So it's a very useful tool for the manager to see the actual conditions. The third example is a textile machine. With the Icomox installation, the machine operator is now able to check the motor conditions easily. The machine is over 30 years old and the manager has not been able to see any motor data so far. By using the Icomox, it will help him to repair the machine before it collapses. How this is working. This graph has some special design. You need to read it from the right side to the left side. In the beginning, after installation, the motor has all parameters in line with the specification. During this stage, we are starting the machine learning. This is the proactive stage, the green marked stage. Through use, the machine behavior is changing over time. The motor might start to make noise, the magnetic field might fluctuate, and you will see vibrations or potentially heat. Through the help of AI on edge, you will get an alarm and information to check your assets. During this predictive stage, you will be able to send technicians before the system will collapse. And for sure, if you repair your machine before it collapses, you will save money. Now Guy will take over and explain you more about the sensors we are using. Thank you for your attention.
Hello, my name is Guy Zohar, and I'm running the R&D in Shiratech Solution. I'm based in Israel, in Tel Aviv area. I will take the technical part of this presentation. So without further ado, let's move on to the Icomox block diagram and dive into the details. Let's take a look at the Icomox top-level block diagram. The heart of the system is an ultra-low power ARM Cortex-M4F from Analog Devices. It is used to control and configure the various peripheral devices, including the sensors, memory, and communication devices. On the left, we can see the set of sensors, which is similar on each of the Icomox models and includes a 3-axis high-precision analog vibration sensor, a 3-axis low-power digital vibration sensor, 3-axis magnetic sensor, MEMS microphone, and temperature sensor. On the upper right corner, we have the communication block, which is different for each of the Icomox models. Icomox Smart Mesh IP is using low bandwidth, high resiliency RF communication standard designed for challenging industrial applications. Icomox NB-IoT is using the public LTE Cat M1 or NB1 cellular network for bidirectional communication with remote server. Icomox PoE is using Cat5 Ethernet cable for both power and LAN connectivity with on-premises or cloud-based service. Below we can see the USB-C type port, which is similar for the 3 Icomox models. For the cellular model, we have a micro SIM connector or onboard eSIM option, a micro SD card for data storage, and the battery to power the wireless model of Icomox SMIP or NB-IoT. The Icomox Microcontroller is CM4050 from Analog Devices. It's an ultra-low power ARM Cortex-M4F. It has 512 kilobytes of internal flash memory used to store the device firmware image and 128 kilobytes of internal SRAM. It has a 12-bit ADC, which is used for sampling the analog accelerometer signal. It uses standard I2C, SPI, and UART interfaces to control and collect data from the sensor and handle the different communication channels. Icomox includes 2 vibration sensors from Analog Devices, ADXL 356 and ADXL 362. The ADXL 356 is low noise, low drift, analog 3-axis MEMS accelerometer used for precision vibration measurement of the asset on which the Icomox is installed. ADXL 362 is ultra low power, low bandwidth, digital 3-axis MEMS accelerometer that can be used as a panic sensor that wakes up the system in case of high vibration pattern while the Icomox is configured for power saving mode. Icomox includes magnetic field sensor BMM 150 from Bosch. It is a 3-axis magnetic field sensor used to measure and estimate the power consumption of the asset on which the Icomox is installed. Icomox also includes MEMS microphone from Infineon. Using the microphone, we can listen to the noise the machine is generating and use this data for advanced pattern analysis. Icomox includes ADT 7410 temperature sensor from Analog Devices. It is a high-resolution 60-bit I2C sensor that can measure the temperature of the asset on which the Icomox is installed using external temperature probe. On this slide, we can see how each of the different Icomox models can be connected to a local on-premises server or cloud service, including Siemens MindSphere, Microsoft Azure, Amazon AWS, and Shiratech Cloud Service, which will be demonstrated in our live demo. On the upper right corner, we can see the Icomox SMIP. It connects to the network through an SMIP gateway that can be based on a PC or Linux machine using our Smart Mesh IP USB dongle. Once the Icomox establishes communication with the Smart Mesh IP gateway, it can be connected to the network using a standard TCP IP connection. The Icomox Narrowband IoT is connected to the public cellular network using LTE, Cat-M1 or NB1. It can be connected to the local network or directly to the cloud service using TCP/IP or MQTT protocol. Icomox PoE is connected to Ethernet switch with PoE functionality to draw power and gain access to the LAN. The connection can be done with Cat5 or above Ethernet cable with length of up to 100 meters. The local edge server acts as a gateway to the cloud platform. It can also run some of the services and analytics to provide near real-time monitoring capabilities. The Icomox end-to-end solution from sensor to cloud is a very flexible solution that can be deployed in various ways to fulfill requirements from different customers. We will now move on to the live demo. Welcome to Icomox live demo. In this video, we will have two demo setups. The first demo includes Icomox PoE connected to Icomox monitor software to demonstrate Icomox anomaly detection module. The second demo includes Icomox NB-IoT connected to Shiratech Cloud Platform to demonstrate the management, analytics, and smart maintenance modules. Let's move on to demo setup number 1. In the first demo setup, Icomox PoE is installed on a 3-phase rotational motor. The motor speed is controlled by an adjustable frequency AC driver. A push button is used to connect or disconnect one of the AC phases in order to simulate an electrical fault. The Icomox PoE is connected to a standard PoE switch using Cat5 Ethernet cable. This cable used to drive 48-volt DC and 100 megabit per second Ethernet communication between the Icomox and the switch. A laptop running Icomox monitor software is also connected to the PoE switch to form a local network with 2 Ethernet devices. On the upper right corner, you can see the live setup, including the AC driver, the phase disconnect push button, the rotational motor, Icomox PoE installed on top of it, and the Ethernet switch. I will now turn on the motor at maximum speed. Let's switch to the Icomox monitor software. On the Icomox monitor software, we can see the sensor data stream coming from the Icomox and transformed to FFT. On this screen, we can see spectrum graphs for all 5 Icomox sensors: the high bandwidth vibration sensor, the magnetic sensor, the acoustic sensor, the low bandwidth vibration sensor, and the temperature sensor. For rotational motor application, we can also see the calculated rotational speed, which is currently around 1800 RPM. And here, this is the anomaly detection module. This module contains 4 presets, which can be trained in different states of the machine. The top bar indicates the anomaly level. It will turn red whenever an anomaly is identified. The 4 bars below indicate the match level for each preset. Right now, preset number 1 is pre-trained for the current state of the motor, which is running at full speed. You can see that the anomaly level on the top bar is 0 or none, and the match level for preset number 1 is maximum, and the bar is colored green. I will now push the red button and disconnect one of the 3 phases connected to the motor. You can immediately hear that the motor sounds different and the spectrum graphs are changing. We see that the anomaly is detected and the anomaly level is at maximum and the indication turns to red. I'm now pushing the red button again to reconnect the phase, and the anomaly is removed. The anomaly indication is removed. Now let's demonstrate the training procedure for a new state. This will make the motor run at about 1500 RPM, and of course create an anomaly, because it is a different state and a different behavior than the one that was trained to preset number 1. I'm pushing the button for preset number 2 to initiate the training procedure, and we can see that the progress bar starts to fill in yellow color. This is indicating that the training procedure is in progress. We will wait a few seconds for it to complete. Once the training is done, the anomaly detection learned this state, and the anomaly indication should be removed. And this is exactly what we see now in the GUI. On preset number 2, the match level is full and is colored green, and there is no anomaly. Now, again, I will disconnect one of the phases from the 3-phase motor. The anomaly indication turns red, and the progress bar is full, indicating the anomaly was detected. I will reconnect the phase, and the anomaly is gone. So to conclude the anomaly detection module, this module can be trained to recognize different operating states of the machine. Whenever the operating condition is different from the trained condition, anomaly indication is showing. I will now turn off the motor. Let's move on to demo setup number 2. In the second demo setup, we have Icomox NB-IoT connected to a textile machine in a factory. The Icomox NB-IoT is connected to Shiratech cloud platform using the public cellular network. The Icomox device is controlled and monitored from the cloud platform. The data that the Icomox sends to the cloud is processed and analyzed to provide the user meaningful insights about the state of the asset which the Icomox is connected to, using customizable dashboards. We will now move on to see Shiratech Cloud Platform. I will just switch to it. Okay. This is Shiratech Cloud Platform. The first screen we see is the management screen. On this screen, we can see the list of available Icomox devices and their name. We can see the connection state. We can see when was the last time the Icomox was connected to the system, and when it is expected to reconnect in case it is in power saving mode. We can also see if the Icomox configuration is synced. Let's take a look at Icomox settings screen. In this screen, we can define the Icomox properties. We can also define the asset properties using the fields in these 2 windows. We can configure the Icomox behavior, especially which sensors are sending data to the cloud and when they are going to send their data. Now we will proceed to the smart maintenance screen. This screen is actually a top-level dashboard providing a list of available assets and their current state. For each asset, we can see the current status, alerts and warning, and maintenance procedure recommendation. For each asset, we can drill down and explore the data coming from the Icomox. This dashboard visualizes the raw data and calculated parameters for the specific Icomox. We can see the calculated KPIs for vibration, magnetic, acoustic, temperature, and speed. We can see two-dimensional graphs for each sensor, and we can also see the spectrum representation in 2D and 3D for each of the sensors. So now we can explore the data to better understand the behavior of the asset. Based on the data and the data analysis for the data that's coming from the Icomox, we can provide recommendation for maintenance procedures needed to be done. This is the smart maintenance module. In this module, we can see recommendations that are specifically designed for each type of asset. In this case, there might be a problem with the stator winding, so the maintenance procedure should be taken. This concludes our demo session. For more information on Icomox platform, feel free to contact ShiraTech team.
Cool, so that concludes our presentation for today. Has there been any questions? I can't see any questions in the chat at the moment. Obviously, if anybody has any, please feel free to ask them. We shall sort of hang around in case somebody has any questions for the next few minutes. If not, I hope everybody enjoyed the presentation and got something useful from it. And thank you for attending.
So I have a question, if nobody else is feeling brave. My question relates to the machine learning aspect of the systems that we've been looking at today, the Icomox and the test and development kits that you were discussing in the video. To what extent is the machine learning algorithm dependent on the particular model of accelerometer being used or a particular set of sensors being used? In other words, if you create a machine learning algorithm and train it, but then have a mix or then change to different sets of sensors, is your machine learning algorithm essentially now got to be retrained, or does it have cross applicability across different ranges and types of sensors?
I would say that your machine learning algorithm fundamentally would continue to work as long as, like I said, the data set, I guess, that it's receiving looks very, very similar. So I guess as long as the bandwidths of the accelerometers are able to provide, the same level of, data. So Analog Devices, for example, has a 10 kilohertz bandwidth accelerometer. Obviously, if your algorithm is looking at, and trying to learn from some of the higher frequencies, obviously, if you ever, an alternative product will also need to provide the sort of the same sort of bandwidths and data sources, but ultimately, yeah, the algorithm should be able to work with different sensors. Cool. Cheers, that Karen.
Thanks, David. Thank you. So, does anybody else have a question for our Arrow representatives and analog devices representatives that are here today? I think it was a very interesting presentation. Certainly provided a great level of technical detail in relation to both the individual sensors and their capabilities, and then the integrated system and the way that the sensors and the devices are connected, right through the comms protocols that are employed, and the user interfaces that are required to make sense of all of this avalanche of data that we are able to generate from such systems. So if there are no further questions, and I note that we're coming up on the hour, what I'd like to do is thank our speakers. I think it was a very interesting presentation, and thank you to Arrow for hosting the workshop, this workshop series. We have further workshops coming up in this series that are sponsored by Arrow. The next one will be at 13:30, that's 1:30, case studies and updates, IoT and AI at the edge, featuring Colin McHale of Intel and Andy Smith of Arrow Europe. Or you can also check out the other workshops that are taking place on the Beyond IoT website at beyondiot.ie. The main stage and the research stage are ongoing, and there are 7 other series of workshops happening throughout the day. So thanks to all for your attendance, and thank you for joining us at Beyond IoT. I hope you have an enjoyable afternoon. Bye-bye.
Cheers, everyone. Thank you very much.